Hello everyone and welcome to Robotics and Aerospace Engineering tutorials. In these tutorials we present real and applicable knowledge of robotics, aerospace engineering, mechatronics, robotics, machine learning, control engineering, etc. In this lecture we will thoroughly explain one very important topic that is not precisely and properly explained in standard textbooks on rigid body dynamics, robotics, and aerospace engineering. Namely, we will explain the concept of direction cosine matrix. This matrix is very important for mathematically describing the rigid body motion, rotations, and other topics that appear in aerospace engineering and robotics. Also, the direction cosine matrix is related to quaternions, which are very important in robotics and aerospace applications. We will cover quaternions in our future video lectures. But before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 300 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot! Okay, let's start. We consider two coordinate systems, E and D, shown in this figure. The coordinate system E is represented by red dashed lines. On the other hand, the coordinate system D is represented by blue dashed lines. The unit vectors that define the axis directions of the coordinate system E are E1, E2, and E3. On the other hand, the unit vectors that define the axis directions of the coordinate system D are D1, D2, and D3. Here, we assume that the coordinate system D is rotated with respect to the coordinate system E. Also, it's very important to keep in mind that without any superscript or additional notation, the components of unit vectors of both coordinate systems are represented with respect to some third reference coordinate system. For example, if E1 is defined like this and D1 is defined like this, then all three projections of E1 and all three projections of D1 are represented with respect to the same coordinate system that is independent of both E and D. This coordinate system will be denoted by O. That is, unless there is a superscript notation, all the vectors are represented with respect to the coordinate system O. Next, let us consider this figure. Over here, we see the unit vector D1 and we see the angle that this unit vector makes with E1, E2, and E3 unit vectors. These angles are alpha 1, 1. This is the angle that D1 makes with E1. Then we have alpha 1, 2. This is the angle that D1 makes with E2. And we have alpha 1, 3. This is the angle that D1 makes with E3. We can use this figure to represent the unit vector D1 in the coordinate system E. We can write D1 as a vector is equal to cosinus alpha 1, 1 times E1, that is, times the unit vector E1, plus cosinus alpha 1, 2 multiplying E2 unit vector plus cosinus alpha 1, 3 multiplying the unit vector E3. Over here, we projected the unit vector D1 onto the axis of the coordinate system E. For example, this projection over here is obtained by scalarly multiplying the unit vector D1 with the unit vector E1. As the result, we obtain the intensity of D1 times the intensity of E1 times the cosinus of the angle between D1 and E1. Obviously, we have d1 intensity times e1 intensity times cosinus of alpha 1, 1. And from this equation, we can obtain the following. We know that the intensity of d1 is 1, since d1 is the unit vector. We know that the intensity of e1 is 1, since e1 is a unit vector, and we only have cosinus of alpha 1, 1. And that's precisely the term over here. Similarly, this term over here is obtained as d1 scalarly multiplying e2. And finally, this term over here is obtained by d1 scalarly multiplying e3. Next, let's project the unit vectors d2 and d3 onto the axis of the coordinate system E. Let alpha 21, alpha 22, and alpha 23 be the angles that the unit vector d2 makes with the unit vectors e1, e2, and e3 of the coordinate system E. Next, let alpha 31, alpha 32, and alpha 33 be the angles that the unit vector d3 makes with the unit vectors e1, e2, and e3 of the coordinate system E. Next, we have d2 can be decomposed like this, and d3 can be decomposed like this. That is, we can represent both d2 and d3 by their projections onto the axis of the coordinate system E. These three equations are very important since they show us how to represent the unit vectors of the coordinate system D by using the unit vectors of the coordinate system E. Furthermore, these three equations are actually defining the direction cosine matrix. In the sequel, I will explain how to form the direction cosine matrix by using these three equations. Here's the direction cosine matrix. The first row of this matrix is simply formed by taking these cosine terms from the first equation and by placing them in the first row. Similarly, the second row of the direction cosine matrix is formed by taking these terms and placing them in the second row. And finally, the third row is formed by taking these three terms and placing them in the third row. Now, if we go one step back in our derivations, we will see that, for example, this term is the cosine of the angle that the unit vector d1 makes with the unit vector e1. Similarly, this term over here is the cosine of the angle that the unit vector d1 makes with the unit vector e2. And similarly, we can interpret all other terms. Furthermore, we can write the direction cosine matrix like this. Basically, we can form the direction cosine matrix by scalarly multiplying the unit vectors of the coordinate system D with the unit vectors of the coordinate system E. Over here, we represented the unit vectors of the coordinate system D by using the unit vectors of the coordinate system E. However, we can do vice versa. These three equations, given over here, represent the unit vectors of the coordinate system E by using the unit vectors of the coordinate system D. We can see the same angles, however, the order of angles is rearranged. In fact, we can define another direction cosine matrix that will correspond to this transformation, and this direction cosine matrix will be a transpose of our original direction cosine matrix. Okay, now let us discuss the properties of the direction cosine matrix. At the beginning of this tutorial, we explained that all the components of unit vectors of both coordinate system E and D should be represented with respect to some third coordinate system independent from the coordinate systems E and D. The third coordinate system is denoted by O. In this coordinate system, the unit vectors have the following components. For example, E1 has the components E11, E12, E13. Similarly, the unit vector D3 has the components D31, D32, and D33. Here, it's very important to properly understand these projections. The unit vectors of both coordinate systems E and D are represented in the same basis. For example, let this coordinate system be our coordinate system O. And let O1, O2, and O3 be the unit vectors of this coordinate system. Now, let this be E1, and let this be D2. This component of the unit vector E1 is actually the projection of the unit vector E1 onto the unit vector O1. Similarly, this component is the projection of the unit vector E1 onto the unit vector O2, and this component is the projection of E1 onto the unit vector O3. Similarly, this component is the projection of D2 onto O1. This component is the projection of D2 onto O2, and this component over here is the projection of D2 onto O3. At the beginning of this tutorial, we derived this equation. Here's the main question. How can we write these equations in a matrix format by using the direction cosine matrix? Let's do that. We will use these projections and these equations to write this equation. So what's happening over here? We simply take D1 and we take its components. Here they are. Then we take E1 and its components and we write it over here. And we do that for E2 and E3. Consequently, the first equation can be written in this vector format. Now, it's easy to show that this vector equation can be represented as a multiplication of this matrix with this vector, where this matrix is formed by taking the unit vectors E1, E2, and E3 and stacking them next to each other. That is, stacking them as columns. By using the same idea, we can represent this equation in the matrix form. Here's the result. And by using the identical idea, we can represent this equation in the matrix form. Next, we can combine this equation, and this equation, and we can write it down as a single matrix equation. And here it is. Next, let's call this matrix as D underline. This matrix is formed by taking the unit vectors D1, D2, and D3 and stacking them column-wise. Next, let's call this matrix as E underline. However, what is this matrix? It is easy to see that this matrix is actually C transpose. That is, this matrix is equal to the transpose of our direction cosine matrix, and consequently the equation 17 can be written like this. Let us interpret the equation 18. The meaning of this equation is that we can take the unit vectors corresponding to the E coordinate system and we can transform them into the unit vectors of the coordinate system D. And we obtain this transformation by multiplying this matrix E from right by C transpose. That is, by using this equation, we can transform the coordinate system E into the coordinate system D. However, how to transform the coordinate system D into the coordinate system E? Let's see how to do that. Over here, I represented the unit vectors of the coordinate system E by using the coordinate system D. By using the same procedure to the procedure used to derive 18, I can derive this equation. I can write my E matrix, and E matrix is defined over here, as D matrix, and D matrix is defined over here, multiplying the direction cosine matrix. And this equation tells you how to go from the coordinate system D to the coordinate system E. Next, let's see what will happen if we substitute the equation 21 in the equation 18. That is, we are substituting E from this equation into this equation. And let's see the result. As the result, we obtain the equation 22. From this equation, we actually obtain a very interesting equation. We obtain that C times C transpose is equal to the identity matrix. This equation has a very important interpretation. This equation implies that the matrix C is the orthogonal matrix, and it implies that the inverse of the matrix C is its transpose. Furthermore, we can show that the determinant of the matrix C is equal to 1. From this equation, we obtain determinant of C times C transpose is equal to determinant of the identity matrix. From this equation, we obtain that determinant of C times C transpose is actually the product of the determinants, and we know that the determinant of a transpose matrix is actually equal to determinant of the original matrix, and we obtain that determinant squared is equal to 1. We have 1 over here since we know that the determinant of the identity matrix is equal to 1. From the last equation, we can conclude that the determinant of C can either be plus 1 or minus 1. However, it can easily be shown that for the right-hand sided coordinate systems, this determinant should be equal to 1. Perfect. Next, let's see how to use the direction cosine matrix to transform vector from one coordinate system to another. Let us consider an arbitrary vector z with the projections in the O coordinate systems. Z is equal to z1, z2, and z3. First, let's compute the projections of the vector z onto the coordinate system E. That is, we want to represent the vector z like this, where E1, E2, and E3 are the unit vectors of the coordinate system E. Let's compute these projections. Obviously, these projections can be computed by scalarly multiplying z by E1, E2, and E3 respectively. Next, let us introduce this notation. We have z with the superscript e. This means that we represent the vector z in the coordinate system E. z1, z2, and z3 are the projections of the vector z onto the coordinate axis of the coordinate system E. Next, we can write this equation like this. How did we derive this equation? Well, we started from this equation and we used the same procedure that's actually used to derive from this equation this matrix form. And as the result, we obtain the equation 30. On the other hand, we can represent the vector z in the coordinate system D. Again, we use the unit vectors d1, d2, and d3, and we compute the projections by scalarly multiplying z with d1, d2, and d3. Next, we can introduce this notation, z with the superscript d. This means that we are representing the vector z in the coordinate system d. That is, by using the projections of the z vectors onto the coordinate axis of the coordinate system d. And from this equation, we can obtain this matrix equation. Our goal is to find an equation that will transform z with the superscript e directly to z with the superscript d. Let us start from the equation 30. That is, let's start from this equation, and over here I wrote again this equation. Now, by substituting e from the equation 21, and let's see where is the equation 21. Here it is. This equation tells us how to relate e and d coordinate systems. We can actually obtain this equation. On the other hand, we have the equation 34. By using this equation and by combining everything, we obtain such an equation. Now, from 36 and 37, we obtain the equation 38. Since the matrix D is invertible, that is, it's non-singular, from this equation we finally obtain Z in the coordinate system D is equal to the direction cosinus matrix multiplying Z in the coordinate system E. This equation is very important. It tells us how to transform the projections of a vector from one coordinate system to another. That is, if we know the projections of the vector z in the coordinate system E, we can multiply the vector z represented in the coordinate system E by the direction cosinus matrix to compute the representation of this vector in the coordinate system D. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.